Hey there, everybody. Welcome back to our last statistics review video. This is number 4, hypothesis testing. I'm very excited about this video. This is the culmination of what we've been talking about, and it is super important. What we learn in this lecture or this review video will come up all the time in data analysis. This is super important. Okay, so let's jump in. All right. So what we're going to do in this video is we're going to talk about this idea called hypothesis testing. Okay. Now, hypothesis testing or a hypothesis test is the method that we use to determine or come to some conclusion about our population by analyzing our sample data. Okay, so just remember, in statistics, we oftentimes start with some population that we want to know about. We want to know something about a total population, like all American workers, all workers in the United States, for example. That's the population. And let's say there's 100 million of them. Okay. We want to know something. We want to know characteristics about that population, but we don't have data on that whole population. So instead, what we do is we collect data on a little sample. All right. So here's our sample. We collect data on our sample and we calculate some basic statistics, let's say a mean, sample mean, okay? And we use our sample mean as an estimate of the corresponding population mean. We use it as an estimate. What we're doing here is we're using what we can learn from our sample to try to draw a conclusion about what is true in the population. Okay. We've talked about this a bunch up till now. Everything that we've talked about culminates in this method, this hypothesis testing, because this is really the method that we use to actually come to a conclusion about what's true in the population. Okay. And really what this comes down to is we are going to specify, we are going to state, we're going to make a claim about what might be true in the population. So when I say we're going to make a claim, I'm going to say we are going to state a hypothesis. A hypothesis is some claim about what might be true in the population, right? We're going to state a hypothesis. And then we're going to use what we can calculate, the information inside of our sample data, to come to a conclusion about whether or not our hypothesis is true or not. Put differently, we're going to come to a conclusion about whether or not our hypothesis is really reflected in the population, or is what we're seeing in our data just occurring by chance. Okay, that's what we're doing in hypothesis testing. All right, so let's jump in. Super important method. All right, so a hypothesis is a claim or a statement about a property of a population. So, for example, let's say we state a hypothesis that workers in the United States make $5.5 per hour. Now, if you remember here, this is a very low hourly wage in today's America. But as you remember, the data set that we're using in our R demos is from a long time ago. Okay, and so this hypothesis is based on that data set. I'm connecting it to that data set. Okay. And so for that data set, we're going to state a hypothesis, a claim. We're going to make a claim about what is true for the whole population. We're going to say that workers in the United States make $5.5 per hour. Now, of course, we might want to say on average here. So let's just say we're adding on average. Okay, so we're making a claim, we're making a statement, a claim about what's true. We're saying that the population average wage is 5.5. We're going to make that assertion. And then a hypothesis test is a method that you're going to learn in this video or review in this video, depending on if you've seen it before. A hypothesis test is a method or a procedure that allows us to test, is this claim true or not? Or more technically, A hypothesis test is a method or a procedure that will allow us to come to a conclusion about whether or not we think it's true or not. It allows us to come to a conclusion about that hypothesis. All right. Very powerful skill. All right. Now, the way that hypothesis testing works is that we will always state two hypotheses. All right. So here in this slide, I'm saying, okay, we're going to make a statement about the population. Let's say we're making a statement that workers in the United States make $5.5 per hour on average. Okay, so that is a statement. That is a hypothesis. But actually, whenever we do this hypothesis testing method, whenever we do that, we're actually going to state two hypotheses. We're going to state something called a null hypothesis, and we're going to state something called an alternative hypothesis. A null hypothesis is always equal to whatever how do I put it? A null hypothesis is always equal to whatever we kind of baseline think. It's always kind of like the uninteresting case. So let's say our null hypothesis is that US workers make $5.5 an hour. Okay. Then our alternative hypothesis is always that whatever our null hypothesis is not true. It's just the opposite. It's everything other than our null. Okay, so if we're going to say that our null hypothesis is that wages in the United States are equal to $5.5 per hour on average, then the alternative hypothesis is that wages on average are not 5.5. So null and alternative hypotheses are always mutually exclusive and exhaustive. By that I mean we're going to state hypotheses where either one or the other is true, that they both can't be true, and there can't be some other third option that's true. A null and alternative hypothesis are always mutually exclusive, they cannot both be true, and exhaustive. There's no scenario that is not reflected in one or the other. Okay, so our null hypothesis here is that wages in the United States are equal to $5.5 per hour. That's our null hypothesis. Our alternative hypothesis is that wages in the United States are not equal to $5.5 per hour on average. All right, that's the null and alternative hypotheses. Now, whenever we state a null and an alternative, there are actually three different ways of stating it. All right, so here's our three different ways. Option 1, option 2, and option 3. I just showed you option 3. So option 3 is where you state the null as being equal to some number. Here in this table, I'm just saying that it equals to 0, but it doesn't have to be 0. It could be any number. Okay. And then the alternative would just be that the population average is not equal to that number, whatever that number is. Again, on this slide, I'm just using the number 0 as a placeholder. It could be any number. Okay, so that's option 3. That's one of the options, is that the null hypothesis is that mu is equal to a number, and the alternative hypothesis is that mu is simply not equal to that number. Okay. Now, an alternative, or a different one, a different option, so let's go to our option 1 and 2. I could state that the null hypothesis is that mu is less than or equal to some number, in which case the alternative hypothesis is that mu would be greater than that number. So one thing you'll notice here again is that these two hypotheses are mutually exclusive. They're mutually exclusive, right? They don't overlap. There is no number, there does not exist a number that is in both of these categories. Okay, they're mutually exclusive and they're exhaustive. All numbers fit either less than or equal to whatever number we state here, or it's greater than whatever number we state here. Okay, so it's exhaustive. It includes all numbers. All numbers are accounted for. Okay, well, alternatively, or another option is we could say that mu is greater than or equal to 0, and the alternative then is that mu is less than 0. Okay, so these are the options. These are the different ways in which we can formulate our null and alternative hypotheses. And how we formulate them, like which option do we choose, is going to be based on the context. It's going to be based on the context. I think that probably the most common is this one, but it is based on the context. In this video, I'll actually use a couple different contexts. I'll show you two different kind of examples in which we state the hypotheses differently. But remember, your null and alternative hypotheses always have to be mutually exclusive and exhaustive, and they're always going to be one of these three options. Okay, so when we do hypothesis testing, we're always going to have a null and an alternative hypothesis. And so when we do this, all right, we're going to start off by specifying our null. Then we're going to collect sample data and calculate our sample mean. And we are going to use these two pieces of information to come to a conclusion about what we think mu is. Now, if you remember, at the end of last lecture, I had written out the equation for a t-statistic. The t-statistic is our sample mean minus the mu, the population mean, divided by the standard error. And if you remember, I talked about how we could use the t-statistic or a z-statistic, depending on the context, right? That we could use the z-statistic or a t-statistic to tell us how far away our sample mean is from the population mean in units of standard deviations, right? That we could use these statistics to tell us how far away our value is, how extreme our value is. Okay, so I talked about that last time, and then I kind of cliffhangered us. I said, well, but we don't know what mu is, so what good is that? We can't calculate our t-statistic. We can't calculate our z-statistic. And so what good is that? Good is this statistic if we don't know what mu is? Well, this is where we're going to pick up. All right. Now, but before we get there, so here in a little bit, I'm going to calculate a t-statistic for you. But I want to explain the intuition behind what I'm doing first. All right. So here we go. I want to talk about the intuition behind testing a null hypothesis or testing a hypothesis. All right, so this is what we're going to do. Okay, so we have our null. This is something we come up with. We specify this based on our context, based on our research question. All right, we specify a null hypothesis. Then we use our data to calculate a sample mean. And now what we are going to do is we're going to ask ourselves a question. And this is actually going to ring a bell a little bit from back when I was talking about z statistics and t statistics. All right, so this is going to ring a bell from last lecture. We're going to ask ourselves a question. Is our sample mean unlikely if the null is true? We're going to ask ourselves that question. Is the sample mean unlikely if the null is true? Remember when we were talking in the last lecture about z-stats and t-stats? We use these to determine whether or not our value, the value of our sample mean, we use them to determine if our value of the sample mean is likely or not likely. Remember when I said that if we have a z-stat really greater than 2, but especially greater than 3, that it's super unlikely. Remember when I said that? Remember when I said that if we have a z-stat and it's really big, that would mean that value, our value, the value that we measured, is really unlikely? Okay, that's where we're picking up here. We're going to ask ourselves this question. We're going to ask, is our sample mean unlikely if the null hypothesis is true? So if we assume that the null hypothesis is true, is our sample mean unlikely? All right, so put that back into the context of last lecture. Think about it now. So let's say we have a t-statistic, all right? And it is equal to our sample mean minus the population mean divided by the standard error. What we're going to do is we will take our sample mean and put it in there, and then we are going to bring in our hypothesized value of mu. That is where this mu is going to come from. We're going to use our hypothesized value of mu and then divide by the standard error, which we can calculate. And if this number is really big, it's a very large number, or very small. By that, I mean very, like very negative. Like if it's greater than 3 or less than -3, and even, frankly, if it is greater than 2 or less than -2, that is going to tell us that our value, our sample mean, is unlikely if the null hypothesis is true. All right, so this is the question we're asking ourselves. We're going to ask ourselves the question of whether or not our sample mean is likely or unlikely in the scenario that the null is true. All right, we're going to ask ourselves that question. Now, we'll say, is the sample mean unlikely if the null is true? If it is unlikely, if it's really unlikely, then what we should do is we should reject the null. That means we should look at our null hypothesis and say, you know what? I don't buy it. I don't believe it. I don't think it's true. If our sample mean is really unlikely under the scenario that the null is true, then we have evidence to reject the null. We have evidence to say, you know what? I don't think the null is true. I don't think this hypothesis is correct. I don't think it's true. I reject it. Okay. Similarly, we're going to ask the inverse question. We'll be asking these two questions at the same time. Is the sample mean likely if the null is true? If it is likely to find a value of, if it is likely that we would find a sample mean like the one that we do find under the scenario that the null is true, well, that would give us evidence to fail to reject. We do not reject the null. So that would be if we calculated our t-statistic or our z-statistic and they were less than, let's say, 2 or greater than -2. So if our t-statistic is not super big in magnitude, well, that means that our sample mean is pretty likely under the scenario that the null is true, in which case we will have no reason to reject the null. We will have no reason to reject the null. All right, that's the intuition. All right, so what we're doing is we're using this t-statistic at our our estimate of the sample mean and our hypothesized value of the mean, all right, to come to some conclusion about what we think mu is. All right, remember, we don't know what mu is. We don't know what's true about the population. We're trying to come to some conclusion about it. All right, and this is the method. Okay, let me dive deeper into that. Okay, I'm not done. If that wasn't clear, hopefully it'll be clear as I proceed. All right, so let's reinforce that intuition. So here we go. We have, here's a probability distribution, a PDF, a probability density function, right? It is the sampling distribution of the mean. All right, the mean or the expected value of this distribution is equal to the true population mean. We know that. Okay, and on the x-axis, we have different values for sample means. Okay, and this particular sampling distribution of the mean, this is the distribution if let's write it this way, if the null hypothesis is true. So what I mean by that is the distribution that you are looking at on this screen right now is the distribution of sample means if the null hypothesis is true. That is, if mu actually is equal to 5.5, this is the distribution that you would find. This is what the distribution would be for the sample mean. All right? And so now we're going to ask ourselves those questions that I showed a moment ago. All right? So let's imagine that we calculate a sample mean, and this is what we find. All right, I didn't actually write in the value here, so I'll just write one in now. Let's imagine that this value here is 5.7. So let's say our sample mean is 5.7. So we would look at our sample mean and we would think about it by comparison to our hypothesized population mean. We'd look at it and we'd say, huh, okay. Uh, if our null hypothesis is true, that is, if the population mean really is equal to 5.5, do we think that this sample mean is likely or unlikely? Like, if mu really is 5.5, is it likely that we would find a sample mean of 5.7? Just looking at this distribution, it sure seems like that would be the case. It seems pretty likely that we would find a sample mean value somewhere close to 5.5 if, in fact, mu is equal to 5.5. So it seems pretty likely. What about this one? I don't know, let's say this is sample mean 4.5. Is this likely or unlikely if mu is equal to 5.5? Well, just by looking at the distribution, it is less likely to find a value somewhere around 4.5 than it is to find a value somewhere around 5.5. So this is less likely, right? It's less likely. What about this one? What if we find a value of let's see, I think this is probably 7.4. If mu is 5.5 and our sample mean is 7.4, would we think that that 7.4 is likely or unlikely? Like, is it, how likely is it that we would find a sample mean somewhere around 7.4 if in reality mu is equal to 5.5? I think we would have to say this one is pretty unlikely. This one's pretty unlikely. This one is pretty likely. This one is somewhere in between. So the intuition here is, if our sample mean, if we find a sample mean that is really unlikely, under the assumption that the null hypothesis is true, if our sample mean is really unlikely, like there's a very low probability of finding a sample mean somewhere around ours, under the assumption that the null is true, if that's the case, then we might begin to ask ourselves, maybe the null is false. We might begin to ask that question. We might begin to think that the null is actually false. If our sample mean is likely somewhere like 5.7, if it's somewhere around here, we don't have any reason to doubt our null hypothesis. Our null hypothesis is that the population mean is 5.5. Our sample mean ends up being 5.7. It's like, wow, you know what? That's pretty close. I bet that our null is true. It's probably true because our sample mean is really close to 5.5, and that's exactly what we would expect if, in fact, the population mean really is 5.5. But if our sample mean is really far away, if our sample mean is way up here, if our sample mean is super unlikely, under the scenario that mu is equal to 5.5, under the scenario that our null hypothesis is true, if our sample mean is really unlikely, then we might begin to ask ourselves, huh, That's pretty unlikely. Maybe the null isn't true. Maybe the null is false. Okay, that's the intuition. That is the intuition behind the hypothesis testing. And so naturally, with this intuition, we're going to have to ask ourselves, like, at what point would our sample mean be so big or so small that we would begin to doubt the null hypothesis? Under what scenario would we begin to doubt it? Like if our sample mean was larger than, let's say, this dotted line, like if our sample mean was somewhere larger than this dashed orange line, would we start to doubt? Like if our sample mean was here, let's say our sample mean was here, would we doubt it? Would we doubt our null hypothesis? Would we begin to doubt that mu is actually equal to 5.5 if we found a sample mean here? Would we? Or what about here? What if it was here, would we doubt it? If it was here, would we doubt it? How unlikely does our sample mean need to be before we begin to doubt our population mean? Before we begin to doubt our null hypothesis? At what point? Where do we begin to doubt our null hypothesis? Is it here? Is it somewhere along here? Is it way down here? How do we know? At what point will we begin to doubt our null? At what point do we need to come to a conclusion and say, nope, I don't believe it. I don't think the null is true. I think the alternative hypothesis is true. How do we do that? Okay, I'm going to answer that question, but that's the intuition. All right, that's what we're doing with hypothesis testing. All right, now just to reinforce some of the language, when we do hypothesis testing, we are always going to come to some conclusion about the null hypothesis. All right, we use the notation H for hypothesis. That little 0 at the bottom, that means a null hypothesis. So null hypothesis. We're always going to come to a conclusion about the null hypothesis. And we're going to come to one of two conclusions. We will either reject the null. That's where we conclude that the null is false. We either reject the null or we fail to reject the null. We never accept the null or conclude with any like with any certainty, I should say. We never state that the null is true or false. We are always going to come to a conclusion of either reject the null or failing to reject the null. If we reject the null, we are going to act under the assumption. We're going to effectively conclude that the null is false, even though we don't know that it's false. We're just pragmatically rejecting it. Okay? Or we will fail to reject the null. That doesn't mean that we are saying that we know the null is true. It just means we're failing to reject it. Okay. We do not have evidence. So if we fail to reject, that means we do not have sufficient evidence to reject the null. So we're going to pragmatically act as if the null is true. All right. So those are our options. We're either going to reject or fail to reject. Reject or fail to reject. And we make that decision on the basis of where our point estimate is relative to the distribution of sample means based on the null hypothesis. So basically, at some point, if our sample mean is so large or so small that we think it's sufficiently unlikely under the assumption that the null is true, eventually we will say, you know what, I reject the null. All right, now how do we do this pragmatically? Like in practice, how do we do it? Well, what we're going to do to test our hypothesis is we are going to construct a test statistic. All right, test statistics, they take on different forms. Sometimes we use z-stats, sometimes we use t-stats, sometimes we use f-stats. In this review, I'm only going to talk about t-stats. This will be the most common. So we're going to talk about t-stats. What we're going to do is we are going to construct a test or a t-statistic. We are going to construct a t-statistic. And if our t-statistic is sufficiently large, or sufficiently small, that is sufficiently negative, if the absolute value of our t-statistic is large enough, then we will reject the null. And if it is not large enough, we will fail to reject the null. Because remember, our t-statistic tells us, it communicates to us how far away our estimate, our sample mean, it tells us how far away our sample mean is from the population mean. And so if it's large enough, that gives us really good reason to doubt our hypothesized population mean, right? That gives us evidence, it gives us reason to reject the null. So what we're going to do is we're going to create a test statistic, a t-statistic, and we're going to use that to come to our conclusion, to either reject or fail to reject the null hypothesis. So the way that it works is we will take our sample mean, subtract the population mean that corresponds to our null hypothesis. That's where this little zero comes in. That represents the population mean that corresponds to our null hypothesis, divided by the standard error, which we know how to calculate. Here's it. Here's how we calculate it. All right. This is going to be our t-statistic. We're going to look at our t-statistic. If it's big enough, then we are going to reject the null. And if it's not big enough, we're going to fail to reject the null. All right. That's how this works in practice. Okay. All right. Now, just to kind of like make the comparison, in the last lecture we talked about z-statistics, and then we briefly introduced t-statistics. A t-statistic is just a value that comes from what's called a t-distribution, and a t-distribution is very similar to a standard normal distribution, but it just has a larger variation. Other than that, same basic idea. It has a mean of 0. It is symmetric on both sides. It just has a larger distribution than the standard normal. All right, so we don't really need to sweat this difference too much. I just wanted to point this out just to make that comparison. Okay, so now let me apply the intuition. I'm going to go a little bit deeper. I'm going to kind of reinforce the intuition and go a little bit deeper using this idea that we are going to calculate a t-statistic and use that to determine whether or not to reject or fail to reject the null. All right, so let's imagine that what you're looking at here is a t-distribution. All right, the mean is 0. It's symmetric on both sides. Okay, we're pretty comfortable with these right for now. Okay. There's our mean. Mean is 0. Okay, so what we are going to do is we will calculate a t-statistic. All right, that's what we're going to do. Now, here's the intuition first. Before I kind of show what our t-statistic might be, let's kind of talk through how to use this distribution. All right, so here we go. Here's the mean. Let's just imagine, just for a moment, I'm just gonna put a line here. All right, this line, it's just the cutoff for a particular t value. I don't know, I put a little asterisk here. It's just some arbitrary value. I'm using it for illustration. So just imagine I have a t-statistic value and it's here. It's not our t-statistic. I didn't calculate this. This is just a value. This is just some arbitrary value on this distribution. I'm just using this for illustration. All right. Now, what I have not mentioned about probability distributions, or PDF, probability density functions, yet, I'm going to need to introduce it now so it's clear. For a probability density function, so it's PDF, probability density function, the way that these functions work is that the area underneath the curve, the area underneath the function, this area is that area is the probability of finding a value, in this case a t-value, within the specified range. So from here upwards, this area underneath the curve is the probability of finding a t-statistic value that is in this range. That's what that area is. And you can do this for any range. So let's say from here to here, this area is the probability the area underneath the curve, this area is the probability of finding a t-statistic value within that range. This is how PDF functions work. The area underneath the curve, the area underneath the PDF function, tells us the probability of finding a value within that range. That's what it is. That's how these functions work. Take my word for it. This is how they work. And we just need to know that to understand the intuition here. All right. So the space below the PDF curve is the probability of finding a value within that range. So if I shaded this area here, you can say, okay, this area here is the probability of finding a t-value that is greater than, of finding a t-value that is greater than t star. The area underneath the curve is the probability of finding a t-value that is greater than this particular t-value represented by the line. And this t star is just arbitrary for now. All right, this is how these distributions work. You can take my word for it. This is how they work. So whenever you look at shaded areas on a PDF, on a function like this, you know that what's being referred to here is the probability of finding a value within that range. All right. Oh, so this actually, sorry, this should be T star. This should be an asterisk here. So this area here, this area shaded in red, this area corresponds to the probability of finding a T value that is greater than T star. So this area here is the probability of finding some T value that is greater than T star. Okay, that's important. You can take my word for it. All right. Now, with that said, just to remind you, the intuition here is that we are kind of asking ourselves, at what point is our point estimate so large that we would doubt our null hypothesis? At what point is our point estimate so large that we would doubt the null hypothesis? We're going to use a t-distribution and our t-statistic to come up with that. All right, at what point? So the way that this works in practice is that we will choose that cutoff. We will choose. We get to choose. You get to choose. When you do research, you get to choose. You get to choose how unlikely our X bar needs to be for you to reject the null. You get to decide. You get to decide how unlikely your X bar needs to be in order for you to reject the null. You get to decide that. Now, the way that we do this, practically speaking, is that we will pick a probability. We will pick a probability to reflect that unlikeliness, so to speak. Okay. And we use the t-statistic to communicate to us how likely or unlikely our sample mean is. So what I mean by that is this. We will calculate a t-statistic for our sample mean. Right? And we will choose how unlikely that needs to be in order for us to reject the null. All right, so let's say here, let's just take a first example. Let's say that we decide that we will reject the null if we find a value. When I say we find a value, I mean our t-statistic, which corresponds to our sample mean, right? All right. Let's say that we decide that we are going to reject the null if we find a value, that is a value of the t-statistic, for which there is less than a 10% chance of finding it when mu is equal to 5.5. So if mu is equal to 5.5, that is, if our null hypothesis is true, we are deciding that we will reject the null if our t-statistic has a 10% probability or less. All right, let me say this again. This is a little complicated. So remember what I said a moment ago. The area underneath the curve corresponds to a probability of finding a value greater than whatever our cutoff is. So let's imagine that we set T star in such a place, like we choose T star in such a place, in such a way, we choose T star in such a way that this area here is equal to 10% or 0.1. If that's the case, then we would say we will reject the null whenever our t-statistic is greater than T star, which means that there is a less than 10% chance that we would see our t-statistic if the null is true. So if the null is true, there is a less than 10% chance that we would see our t-statistic. All right. So what we're saying is if there is a probability of less than 10% that we would see our t-statistic under the assumption that the null is true, then we would reject the null. We would decide, pragmatically, we would decide that we don't think the null is true and we're going to reject it. All right, so we could do that. We could set a threshold. We could choose that we're going to reject the null so long as our t-statistic is less likely than 10%. We could set 10% as our threshold of unlikeliness. Okay, in which case, if we got a t-statistic here, we would fail to reject. If we chose a 10% unlikeliness, okay? If we chose 10% and we got our t-statistic was here, well, we would fail to reject. But if our t-statistic was here, we would reject. All right? And we chose this. We chose this threshold. And so in this case, if we choose 10%, then if our t-statistic is here, we will fail to reject. But if our t-statistic is here, we will reject. We're saying that any t-statistic that is more extreme than this cutoff is unlikely enough that we will reject it. But any t-statistic that is less than it is not unlikely enough, and we will fail to reject. Okay. All right. Now, we could choose different thresholds. How about this one? This one would correspond to 5%. In this case, there's a 5% chance of finding a value that is below this T star. In which case, we would, if our t-statistic was here, again, we will fail to reject it. If our t-statistic is here, we would reject it, right? If our t-statistic is more extreme, farther away, less likely than our cutoff, then we will reject it. And in this case, we've chosen a cutoff of 5%. We will reject any t-statistic. We will reject the null if we have a t-statistic that is less than 5% likely to occur under the assumption of our null hypothesis, right? We'll reject our null if that's the case. But we could be really strict. We could set a cutoff of 1%. You can see how we keep getting smaller here, right? We could set a cutoff at 1%, and if we did that, we would actually fail to reject in both cases. That is, we would say this t-statistic is not unlikely enough for us to choose to reject, and so we're going to fail to reject. And so you get to choose. You get to decide the cutoff. You get to decide how extreme does your t-statistic need to be in order for you to reject the null hypothesis. All right. Now, in practice, pragmatically, this percentage, this area, this percentage, we call this the significance level, or alpha. Often we'll use the Greek letter, the lowercase Greek letter alpha, to refer to this percentage. And we call it a significance level. And we choose our significance level. Typically, in practice, we will choose one of these three options. And these are the three that I actually just walked through. We will choose a 10% cutoff, a 5% cutoff, or a 1% cutoff. And even more practically speaking, when you're doing this in practice, when you get your t-statistic, you will indicate if you reject the null at 10%, or if you reject the null at 5%, or if you reject the null at 1%. Okay, so these are the significance levels. These are the possibilities. These are the possible cutoffs. All right, so just to go back through, here's a cutoff of 10%, here's a cutoff of 5%, here's a cutoff of 1%. Oh, this is typo, 1%. Okay, 10%, 5%, 1%. So if you choose a cutoff of 10%, any t-statistic larger than this, if you get a t-statistic larger than this, you will reject the null. If you choose 5%, any t-statistic larger than this, you will reject the null. If you choose 1%, any t-statistic larger than this, you will reject the null. So reject, fail to reject. Reject, rejected 5%, rejected 10%. Rejected 10%, rejected 5%, reject at 1%. Now, in practice, pragmatically, to be very clear, what we actually do, practically speaking, is that we will find our t-statistic, and then we will calculate the probability of finding a t-statistic greater than our t-statistic. We're going to calculate the area underneath the curve beyond our t-statistic, right? And that probability is the probability of finding a t-statistic greater than our t-statistic. We're going to calculate that, and we're going to call that a p-value. And we will reject the null if our p-value is less than our chosen alpha. So that's practically speaking what we do. And we use computer software to do this, so it's actually it's really not terribly difficult. We choose an alpha, we calculate a p-value, Our p-value is based on our t-statistic. The p-value is the area beyond our t-statistic under the curve. And if our p-value is less than alpha, we reject the null. That's it. That's the practical step. That's how this works. Let me review this. So kind of go through the steps. Step one is we state a null hypothesis. That's always going to be motivated by our research question, but we're going to state a null hypothesis. Step two is to collect sample data. So in this case, we're going to collect sample data from US workers. Step three is we'll calculate a t-statistic. Step four is we choose our significance level. It's always going to be 0.1 or 0.05 or 0.01. All right, you're going to choose, let's do it this way. You're going to choose a significance level. Then you're going to take your t-statistic and use it to calculate a p-value. All right. Again, the p-value is the probability of finding a t-statistic beyond yours. All right. You're going to use a statistical software for this. All right. So it's not hard. Okay. Then you are going to look at your p-value that you calculate using a statistical software. And if your p-value is less than your chosen alpha, you're going to reject the null. If your p-value is greater than or equal to your chosen alpha, you will fail to reject the null. And then using statistics language, if you reject the null, you conclude that whatever you find is, quote, statistically significant. And if you fail to reject the null, you're going to say that whatever you find is not statistically significant. Okay, I want you to look at this carefully for a second. What you are looking at right here is probably the most important thing from all the review videos. This this culminates, it encapsulates a lot of what we've learned so far. A lot of what we've learned so far kind of culminates in this slide, this procedure. But if there's one thing that you learned from this review, remember this. Remember how hypothesis testing works. Remember that we always state hypotheses. We use our sample data to calculate a test statistic or a t-statistic. We have some sort of idea about what threshold of significance we're using. We calculate a p-value using software. And then most importantly, right here is the decision, is how the decision works. Remember this. This is so important. Sear this in your memory. The way you make your decision is you will compare your p-value to your chosen alpha. And if your p-value is less than alpha, then you reject the null. If your p-value is greater than or equal to alpha, you fail to reject the null. Okay. Now, I need to go to the next thing. All right, there's another important thing. Let's keep building off of this. So one thing that you might recognize already is that when we make decisions about our hypotheses, we don't actually know if they're true. Like, we don't know if we're correct or not. We're just making a decision. We're choosing to reject the null or not reject the null, but we don't know if we're correct or not. What I mean by that is we can commit errors. We can choose to reject a null hypothesis when in reality the null is true. We also could fail to reject the null hypothesis when in fact the null hypothesis is false. That means when we come to these conclusions, when we make our decisions, we can be wrong. It's really important to recognize that we can actually be wrong about our decisions. Right? Remember, the null and alternative hypotheses are making competing claims about reality. That is, they're making competing claims about the population. And either the null is true or the alternative is true, but both cannot be true and both cannot be false. Remember, they're mutually exclusive and exhaustive. So it is one or the other. Either the null is true or the alternative is true. It is one or the other. And we are going to make a decision. We're going to choose. We're going to make a pragmatic choice. We're going to go down this road or this road. And it's one or the other, and we have to pick. Which road are we going to go down? Are we going to go down this road and then conclude the null is true? Or are we going to go down this road and conclude the alternative is true? We have to pick one or the other. If we pick that the null is true, we could be wrong. If we pick the alternative is true, we could be wrong. All right? That is what we call error. And there's two different kinds of error. There's type 1 error and there's type 2 error. And we can commit errors. Type 1 error is when the null hypothesis is true, but we reject it. That is a type 1 error. If, in fact, the null hypothesis is true, but we reject it, we are committing a type 1 error. So in this case, we have wrongly concluded that there is a statistically significant difference or effect or whatever it is we're trying to measure, when in fact that is not the case. That is a type 1 error. A type 2 error is the opposite. A type 2 error is when the null hypothesis is actually false. That means when the alternative hypothesis is true, but we fail to reject the null. So in that case, we are concluding that there is no statistically significant phenomenon in our data, that there is nothing, we're not rejecting the null, we're failing to reject the null, but the null is actually false. We're walking down the road as if the null is true, but in reality, the null is false. That is type 2 error. So one way to think about it is to look at this table. Okay, so in the columns, you'll see statements about reality. It's possible that the null is true, and it's also possible that the null is false. We don't know which one is true, right? We don't know if the null is true or not. We're trying to make a judgment call. Okay, so either the null is true or the null is false. And we are making a decision. So this is our decision. This is our decision, and this is reality. Either the null is true or the null is false, and we are making a decision. So if the null is true in reality, and if the null is true in reality, and we reject it, if we choose to reject it when it's actually true, we've committed type 1 error. If in reality the null is true and we fail to reject it, that means we effectively conclude that it's true. If we fail to reject it, well, then we're correct. We've made a correct decision. Our decision reflects reality. If the null is false, so if the null is false and we reject it, if the null is not true and we reject the null, well, then we're correct. Our decision corresponds to reality. But if the null is false and we fail to reject it, then we've committed type 2 error. And our decision does not reflect reality. So you can see our decision can be correct or it can be incorrect. This should be a little troubling. It's a little troubling that when we do hypothesis testing, we will come to conclusions, but our conclusions can actually be wrong. Okay. So when we do research, practically speaking, when we do research, we're going to try to avoid errors as much as we can. Okay. So just to bring this into our example, type 1 error would be, in reality, wages are actually equal to 5.5. So remember our null was population mean is 5.5. So type 1 error is, in reality, wages are equal to 5.5. But in our analysis of our sample data, we conclude that wages are larger. That is, we reject the null hypothesis. Type 1 error is when wages really are equal to 5.5, but we have rejected the null. That's a type 1 error. Okay, that's type 1 error. Type 2 error is, imagine in reality wages are actually greater than 5.5. But in our analysis, we find that wages are not significantly larger, so we fail to reject. That means that in reality, mu is larger than 5.5, but we don't reject the null, which means we're effectively concluding that the null is true. That's type 2 error. Type 2 error is when we pragmatically operate, we come to the conclusion that we should act like the null is true, when in reality, the null is actually false. That's type 2 error. That's type 2 error. Okay. All right. Now, we can reduce the chances of committing type 1 error by choosing a smaller alpha. We can reduce the chances of committing a type 1 error by choosing a smaller alpha. But on the flip side, we can reduce our chances of committing type 2 error by setting a larger alpha. So what we can see here is that there is a trade-off between type 1 and type 2 error. If we choose a smaller alpha, let's say alpha equals 0.01, it is very unlikely that we're going to commit a type 1 error. But it also becomes more likely that we commit type 2 error. Okay, so there's a trade-off. Now, there's other ways to try to reduce these errors, but it's outside of the scope of this conversation. So right now, we just need to kind of recognize that type 1 and type 2 error are kind of in tension with each other. And if we want to reduce type 1 error by setting a smaller alpha, we actually increase the chances of committing type 2 error. If we want to reduce the chances of committing type 2 error by choosing a larger alpha, we increase our chances of committing a type 1 error. So, practically speaking, we oftentimes we'll have to try to decide, well, which one matters more? Which one do we care about more? Okay. All right. Now, with that said, let me just kind of give an example. I'll kind of apply what I've talked about just to make this a little bit more concrete. So let's say we're doing some policy evaluation. We're trying to figure out if a particular policy works. All right, so let's imagine that one school district has implemented a program. And the program is so a policy, a school district has implemented a policy where they will now provide free school lunches to all their students. All right, so here's one school district, and they have introduced a new program, a new policy. And we have a similar school district, maybe nearby, that doesn't implement this policy. So in that school, students still have to pay for their lunches. And we're interested to know, is this a policy? Is this policy effective at helping students, let's say, with their test scores? Does this policy help to improve students' test scores? That seems like a pretty good question. Does the school lunch program improve test scores? That sounds like a pretty interesting and policy relevant research question. And we can use hypothesis testing to answer this question or to come to some conclusion about whether or not this policy was effective. Okay, so how does that work? So again, here's the scenario. We have a research question. Do school lunch programs improve SAT scores? There's our research question. We have one school district that implemented a free lunch program, another similar school district that did not. And when we look at those two school districts, we can see that the SAT score in math, and let's just say that's what we're focusing on, that the average SAT score in math in both districts before the program was 450. All right, here's our scenario. This is our policy analysis scenario. We're going to use hypothesis testing to test this. All right, so what we need to do is we need to state a null and an alternative hypothesis. And remember, they have to be mutually exclusive and exhaustive, and they should follow one of these three options. Now, I'm going to go just a little deeper than I went a moment ago. When we state a hypothesis, we're always going to state either a one-tail test or a two-tail test. A one-tail test is when we are looking for an increase or a decrease. A two-tail test is when we are looking for any difference. So remember our research question here. Do school lunch programs improve SAT scores? So when you read that question, you know that we are doing a one-tail test. That is, we are asking the question, do school lunch programs increase test scores? All right. If that's what we're looking for, then we will come down here and we need to write hypotheses that correspond to it. If we're looking for an increase or a decrease, that means we have a one-tail test. One-tail test just means we're looking only at an increase or only at a decrease. All right, so now we're here. We need to pick a one-tail test. We need to set up our null and alternative hypotheses according to a one-tail test. And we need to ask ourselves, do we want an upper tail test or a lower tail test? How do we do that? Okay, so earlier I was a little bit vague about how we define our null hypothesis, but now that I have a kind of a good example illustration, I can be a little bit more precise as to how we define our null and alternative hypotheses. Okay, the way that this works is that the null hypothesis is always, this is the way I like to say it, the null hypothesis is always that what we're looking for isn't there. That what we're looking for isn't there. What we are looking for isn't there. So in this research question, we're asking, do school lunch programs improve SAT scores? So if that's our null hypothesis, if that is our research question, then our null hypothesis should reflect that school lunch programs do not increase test scores. That means mu should not, the null hypothesis should be that mu is less than or equal to whatever this number should be, whatever this number is. Remember, in this table, I'm just using 0 as a placeholder. We need to write our own. So in our research question, all right, do school lunch programs improve SAT scores? Remember, beforehand, before the program went into place, SAT scores on average was 450. So what we would do here, the null hypothesis, is that there is no increase. That what we're looking for isn't there. We're looking for an increase. So the null hypothesis is that there is no increase. That is, that the population SAT score for math on average is less than or equal to 450. It's not any bigger after the program's implemented. That's the null hypothesis. The null hypothesis is that the SAT scores after the program is implemented are not bigger than 450. That's the null. What we're looking for isn't there. The increase isn't there. That's what the null is. So then the alternative is the opposite. The alternative is what we're looking for. We're looking to see, is there an increase? And so the alternative is mu is larger than 450. So this would be our null and alternative hypotheses for this research question. We're doing an upper tail test. We are looking for an increase. We are going to test the null hypothesis that there is no increase in SAT scores after the program went into place. That's what we're doing. That's what we're testing. Okay. Now, if the research question was, do school lunch programs decrease test scores? Then we would do a lower tail test, and we would set up the hypotheses in the exact opposite. If the research question was, does a school lunch program affect test scores in any direction, either increase them or decrease them? Is there any difference? Then we would do a two-tail test, where we'd set up the null hypothesis by saying that the test scores are equal to 450 on average, and the alternative is they are not equal to 450. On average, they are larger or smaller. That's a two-tail test. In this case, because of the way the question is worded, because we're only looking for an increase, we are going to do the upper tail test, a one-tail test, upper tail test. So this is ours. These are our hypotheses. Okay. Once we've set up our hypotheses, we will go through, so you can see here, there's our hypotheses. We're just going to go through our steps. Okay. Now, using this case, I just want to explain again what type 1 and type 2 errors are. So a type 1 error is, in reality, school lunches do not increase SAT scores, but in our analysis, we reject that null. So practically speaking, if we commit a type 1 error in this context, let's just think about this practically. Right now, we are evaluating the impact of a school district's policy of giving away free lunches. We are trying to determine, is this school lunch program effective at increasing students' test scores? We're trying to learn that. Why would we do that? Why would we care? Well, if the school lunch program does increase test scores, well, then the school should probably continue to implement the policy. And maybe other schools should implement this policy. Okay, alternatively, if the school lunch program does not improve test scores, well, maybe the school district should discontinue the policy because maybe it's not working at helping the school achieve its goals. Okay, so this matters practically. And so a type 1 error has practical implications. A type 1 error is when the school lunch programs actually don't work. That means schools are wasting their money on a program that is ineffective. Okay, and a type 1 error is when we as researchers conclude that the school lunch program is effective when in reality it's not. And so if we commit a type 1 error, then what we're going to say is, hey, school districts, keep going. Offer free lunches. And hey, all you school districts that don't offer free lunches, you need to go and offer free lunches. You need to go and spend money offering free lunches because this works. That's what we would say. But we would be wrong. And so we would be giving policy advice for schools to go and do things that are ineffective. That's type 1 error. Type 2 error is the opposite. Type 2 error is when free lunches actually do improve students' test scores, but we come to the conclusion that they don't. And so we go and we tell the school districts, hey, you guys, this program doesn't work. You should discontinue it. And then the school districts stop implementing a program that actually helps their students. That's type 2 error. So you can see now that we have a practical example, now that we have a practical policy relevant example, you can see why type 1 error and type 2 error are actually big problems. Type 1 error, if we commit type 1 error, then what's happening is we're going to go out and tell school districts to waste a bunch of money on something that doesn't work. If we commit a type 2 error, then we're going to go to school districts and we're going to tell them to discontinue an effective program. In either case, people are hurt by these errors. And so when we do policy analysis, we need to be careful as best as possible to try to avoid type 1 and type 2 errors. And we need to exercise judgment or wisdom to try to determine which one of these errors is a bigger problem. Because remember, when we choose our alpha, we can determine or influence the chances that we're committing type 1 or type 2 error. So we have to use judgment. We have to use prudence to help us determine which one of these errors is a bigger problem. Okay, so with all that said, here's our steps. State the null hypothesis, collect our data, calculate our t-statistic, choose our significance level, calculate our p-value using the statistical software, and then come to our conclusion using this method. All right, again, sear this into your minds. This is super important. If you learn one thing from all of this, learn this. All right, now I just want to do a slight variation on this. It's also very important, and then I'll be done. Well, at least I'll be done with the lecture slides, and we have to go to an R tutorial. Okay. So oftentimes when we do hypothesis testing, we're actually going to do a hypothesis test about the difference between two means. In the previous example, we stated a hypothesis just about whether or not a particular mean is different than a given number. But in practice, oftentimes we're going to compare two different means with each other. So in this case, what we would do is something like this. So if we apply it to the same context, we might ask the question, is the average SAT score for students that get the free lunches? So let's ask it like this. We might state a null hypothesis like this. We might say that the average SAT score for students with free lunches is equal to the average SAT score for students who do not have free lunches. Right? And we can rewrite this as the average value with free lunches minus the average value without free lunches equals 0. We might ask this question instead. And in this question, what we're doing, or we might say this is a null hypothesis instead. And what we're doing here is we're actually comparing two groups. Instead of comparing the group with the free lunches to just a number, we're going to compare the two groups. We're going to compare the average test scores for the students that get the free lunch to the average test scores for the students that don't get the free lunch. And our null hypothesis is that there is no difference. So the null is that there is no difference. And the alternative would probably be that that there is a difference. Free lunch, no free lunch, but there is a difference. Of course, we also could write our hypotheses like this. We could say less than or equal to or greater than. Okay, so basically what I'm saying here is we could just do this hypothesis test instead, where the hypothesis is about a difference between two means instead of just about a single mean. Other than that, it's basically the same idea. You would just state your null hypothesis about the difference between two means, and then you go through the same steps. Here's your t-statistic. It's just a little bit more complicated. The standard error equation is more complicated. You don't actually need to worry about learning this equation. You're not going to do this by hand. Software is going to do it for you. Here's your t-statistic. Your t-statistic is, here's the mean difference between two sample means minus the hypothesized mean difference divided by the standard error. So it's actually exactly the same equation, except instead we're doing a difference between two means instead of single means. This is actually very common, but we actually go through exactly the same steps. All right. Okay, everybody. Thank you so much for persevering through that. Now let's jump over to R for an R tutorial. Okay, so here we are in R for our review number 4, hypothesis testing. Okay, so we're just going to do a couple quick exercises in R to kind of get comfortable with some of the concepts that we just talked about, but kind of in an applied context. Okay, so here I'm just kind of starting off with a fresh window. I do have my notes open. I'm going to go ahead and just inform R that I want to use a couple packages. And I am going to also import our data set. I'm going to use a slightly different data set. I'm going to call it wages. Again, that's the name I'm going to give it. But you'll notice here that I'm using the wages2 file, just because it has a different variable in it. Now, anytime you open up a data set, you always like to report some descriptive statistics. So let me report some descriptive statistics. We have wage, education, experience. We have the female variable again. And this time we have a variable called job. Let's open up the data set and kind of see what that is. Okay, so this is a variable that indicates what sector the person works in out of a couple of different options. So we've got people that work in manufacturing, management, sales, the service sector. Okay, so a few different sectors that people might work in. Okay, so what we're going to do in this demo is we're going to try to answer 2 research questions. Okay, so the first question is, do people with a high school diploma, do they earn higher wages than those without a high school diploma? So here we're kind of asking, does getting a high school diploma help people earn higher wages? That could be important. That could be important for policy. You know, if that's true, then maybe it would be important for us to try to implement policy to help people get more education. All right. The second question is, do people who work in manufacturing, in the manufacturing sector, earn higher wages than in other industries? That also could be relevant. Okay, so we're going to try to answer those questions using the skills that we just learned about hypothesis testing. All right, so for each question, what we're going to need to do is we need to specify a null and alternative hypothesis. All right, so let's do question 1. Do people with a high school diploma earn higher wages than those without? Okay, now remember, the null hypothesis is always that what I'm looking for isn't there. So I'm looking to see, do people with a high school diploma, do they earn higher wages than those without a high school diploma? So how do I put that in kind of null hypothesis language? Well, what we would say is mu for those with a high school diploma, well, I'll just say HS. So what we're saying here is that the average wage for those with a high school diploma is less than or equal to the average wage for those without, let's just say without a high school diploma. That's how I would state that. The average wage for those with a high school diploma is less than or equal to the average wage of those without a high school diploma. Right? That's the null hypothesis, because what I'm looking for is to see if their wages are higher. That's what I'm looking for. I'm looking to see if that's true. So the null hypothesis is that that isn't true. Okay, so the null hypothesis is that those with a high school degree have less than or equal to the income or the wage of those without a high school diploma. And then the alternative hypothesis is that what I'm looking for is there. That is, that those with the average wage of those with a high school degree is greater than the average wage of those without. So these would be my hypotheses. Now, one thing you'll notice here is that I actually need to test this hypothesis as a hypothesis test about the difference between two means, because here I'm comparing two different means. I'm comparing the mean wage of those with a high school diploma to those or to the average wage of those without a high school diploma. So I need to set this up as a difference between two means. So I'm just going to set this up slightly differently. I think the first way is a little bit more intuitive, but what we're going to do here is we're going to set it up as a difference. Okay? Set it up as a difference, but the exact same idea holds. All right, so here are our hypotheses. And so what we're going to do is we're going to test the null hypothesis, right? And we're going to see if we reject or fail to reject it. All right, so that means what we're going to do is we're going to compare. We're going to test this hypothesis, right? This hypothesis has to do with what we think is happening in the population. But what we're going to do is we're going to use information from our sample to test this hypothesis and see if we will reject or fail to reject it. Okay, so what we need to do is we need to compare the mean, the sample mean the sample mean of the wage variable for those with a high school degree to the sample mean of the wage variable for those without a high school degree. Okay, and then we're going to do a t-test. We're going to do a test. We're going to do one of these hypothesis tests. We're going to get a p-value, and then we will conclude whether or not we will reject or fail to reject the null. Okay, so let's do that step by step. First, we'll just notice that in our data set, we have an education variable that indicates how many years of schooling someone has. We don't have a variable that indicates whether or not they have a high school diploma, but we could probably assume that if someone has completed 12 years of schooling, that they have a high school diploma. So let's do that. Let's create a new variable. It'll be a dummy variable, and it will equal 1 if they have 12 or more years of education, and it will equal 0 if they have less. So this will be a dummy variable, right? And it's a dummy variable that equals 1 if they have a high school degree, and it will equal 0 otherwise. All right, so it's a dummy variable. I'm going to call this variable high SC, so for high school. Okay, now what I'm doing here, let's just make some room. Okay, what I'm doing here is in the wages data set, I'm going to create a new variable called high school. And I'm going to set it equal to this equation here, or this function here. Now, what this is, the way this works is I have a function, it's called if else, right? And with the if else function, what I'm going to do here, I'll write it out here and kind of walk you through it step by step. Okay. Okay. If else, all right. What I need to do is I need to set a condition. So if the education variable that is inside of the wages data set, right? So wages data set, inside of it, the variable education. So if the education variable inside of the wages data set is greater than or equal to 12, then I want this new variable to equal 1. And otherwise, I want it to equal 0. Okay, so actually, I'm just going to get rid of the one I wrote before. So I'm going to create a new variable, and it's going to equal 1 if the education variable is 12 or larger. All right, let's run that. Now let's check it out. Did it work? It did. There it is. Here we have a new variable. It contains ones and zeros. All right, ones indicating they have a high school degree and 0 otherwise. Okay, excellent. That worked. Now what I'm going to do is first, I just want to see what the sample means are. So what is the sample mean for wages for those that have a high school degree? And what does the sample mean for wages for those that don't have a high school degree? So let's just check that out. We actually saw this in a previous video where we're just calculating the conditional mean. All right, so we're going to calculate mean wage by, I'll actually write this out, high school degree. Okay, so just going to repeat a code that we've seen before. All right, so what do we see here? Those with a high school degree have an average wage of 6.4, and those without a high school degree have an average wage of 4.1. Now, the question is this observed difference? So we can see there's a difference, right? There's a difference of roughly 2.4. Is that difference due to just by chance, or is that difference is that difference reflective of a difference in the population? That is, when we look at this, can we conclude that there really is a higher wage for those with a high school degree as compared to those without? In order to do that, we need to do a hypothesis test. Now, we know from the lecture that in order to do a hypothesis test, we have to specify our hypotheses, right, which we have here. We then need to collect our data. We already have the data. We need to calculate our t-statistic, and then we need to calculate our p-value, right? And then we will make our decision about whether or not to reject or fail to reject the null hypothesis based on our p-value, right? Based on how our p-value compares to our significance level, alpha. Well, in practice, how we do that, so practically speaking, pragmatically, what we do is we use a computer software to do that. So actually, we just run a line of code, and what this code will do is it will give us the mean of both samples, so the mean for wage, the mean wage for those with a high school degree, those without a high school degree, and it'll show us the difference, and it will give us a p-value that corresponds to a hypothesis test. So all we're going to need to do is run the code. We will find our p-value, and then based on our p-value, we can decide whether or not to reject or fail to reject. Okay. Now, this hypothesis test, we're going to use a t-statistic for it, so it's actually called a t-test. So we're going to use the t-test command. And what I'm going to say here is that in the wages data set, I want to compare the wage variable. Okay, I want to compare the wage variable between two categories, and the two categories are defined by the high school variable also inside of the wages data set. Okay, so that's what this line does. So what we're going to do is I'm going to run this, and it's going to report what I mentioned. Okay, so here's the output. So this output is for a t-test for the difference between two means. Okay. What we see down here is we see the average wage for those without a high school degree and the average wage for those with a high school degree. So that's down here. All right. And then up here, we see our t-statistics. So this is our t-statistic for our t-test. And then over here, we have our p-value. Our p-value, that is what we use to make our decision. Remember, that's the most important part, right? We have to make our decision. All right, so we're going to make our decision, right? And remember, the way we make our decision is we compare our p-value to our alpha. Okay, if our p-value is less than alpha, then we will reject the null. If it's not less than alpha, we fail to reject. Now, we didn't pick an alpha. We could, remember, the standard alphas are either 0.1, 0.05, or 0.01. Now, sometimes we pick an alpha in advance, but actually most commonly what we do is we look at our p-value and we see, is it smaller than any of them? If it's smaller than any of them, we say that, we report that. We say, okay, this is statistically significant, or we reject the null, and then we specify the level at which we reject it. So what I mean by that is that in practice, this practically speaking, if our p-value is less than, let's say, 0.1, but not less than 0.5, or sorry, 0.05, we would say that we reject the null at the 10% level. We would say that. All right, so if that's the case, what do we do here? Our p-value is less than 2.2 to e to the negative 16. That means it's very small. Just to give you an idea here, that number is 0.00000. All right, I'm going to do 15 zeros. I stopped counting actually. 2. That's what that would be. I don't actually know if that's 15 zeros. I didn't count it out, but it's a very small number. Okay, so then the question is our p-value less than 0.1? If so, we can reject at the 10% level. Okay, good. Is it less than 0.05? If it is, then we can reject at the 5% level. Okay, is our p-value less than 0.01? If yes, then we can reject at the 1% level. And so in this case, is it less than 0.01? Yes. So our conclusion is that we reject at the 1% level. We reject the null. The null hypothesis says that the average income for those with a high school degree minus the average income for those without a high school degree is less than or equal to 0. All right. Put differently, this says the null hypothesis says that the average income for those with a high school degree is less than or equal to the average income of those without a high school degree. And we are rejecting that null. In which case, we come to the conclusion. So our conclusion is that those with a high school degree make more money on average. So there's our conclusion. And that might have policy implications. You know, that might be evidence that suggests that, well, we should invest in education. Okay, let me run another example. So let's say we have question 2. So question 2 is, let me just put this down here. All right, question 2 is, do people who work in manufacturing earn higher wages than those who work in other industries? Well, let's test it. All right, so first we need to write our hypotheses. Oops. So let's say the hypothesis is that, sorry, the null hypothesis is always that what we're looking for isn't there. So the null hypothesis is that those working in manufacturing have incomes less than or equal to those in other industries. And the alternative is always what we're looking for. So that is that average wages for those in the manufacturing sector are greater than those outside the manufacturing sector. Now, of course, we would have to write this as a mean difference because that's what we're doing. We're going to do a test for the difference between two means. And so this right here, this would be the way we would write it. Okay. All right, so we're actually setting these up very similarly. This is a one-tail test. You'll remember from the slides, this is a one-tail test because we're only looking for an increase. Okay. All right, so what we'll do is we'll do exactly the same thing. We will create a dummy variable, binary variable that indicates who works in manufacturing. All right, so actually here, preliminarily, I created a table to indicate how many people, so a frequency table, to indicate how many people work in the various sectors. I also created this new variable called manu, or manufacturing, right? And it indicates who works in manufacturing. Okay, so then I'm going to run my t-test. All right, here's my t-test. So here's the average wage that for those who work outside of the manufacturing sector. And here is the average wage for those that work in the manufacturing sector. All right, here's our t-statistic. And most importantly, here's our p-value. Now remember that we have to make a decision, right? And our decision is that if the p-value is less than alpha, we will reject. So let's look. Here's our p-value. Is this p-value smaller than any of the standard alpha thresholds? No. So what is our conclusion? What's our conclusion? Our conclusion is fail to reject. Those who work in manufacturing do not make more money than those outside manufacturing. Okay, there's our conclusion. Okay, I'm actually just going to wrap it up there today. This is a very quick R tutorial, but it kind of shows you what this looks like in practice. Even though the slides and the concepts were actually fairly complicated, in practice, hypothesis testing is very normal and actually pretty streamlined using statistical software. Really, you just have to make sure you set up the test correctly. You want to understand the test that you're running. That is, you should know your hypotheses. And then you need to know how to interpret a p-value. Okay, we see this a lot in data analytics. This is very important. All right, well, great, everyone. I hope you have a great day. Thank you so much for persevering through a long lecture. And good luck with everything, and I will see you soon. Okay.